Go to the Control Charts menu in your statistical software, and you are flooded with options. IMR, Xbar-R, P-chart, U-chart, Laney U-prime, the list goes on. For many project leaders, this is a statistical nightmare. They ask themselves, which chart do I choose? If you pick the wrong control chart, your statistical limits are calculated incorrectly, your alarms are false, and your process stability is a complete illusion. But choosing the right chart isn't a guessing game. It follows a strict, elegant, binary decision tree based entirely on the DNA of your data.
So, to navigate this tree, we've got to start by splitting the entire world of data into two foundational pillars. On the left side, we have continuous data. In Dutch operational terms, think meten van tijd, gewicht, lengte. We're measuring exact physical parameters here, right? Things like time, weight, or length. Then, on the right side, we have discrete data. Tellen van fouten, pass-fail, defective. This is where we're counting errors, looking at binary pass or fail conditions, and tallying up specific defects. The chart you ultimately need? Well, it depends entirely on which side of this divide your data actually lives.
Okay, Section 1, the continuous data pillar.
This is where we're dealing with infinite possibilities. You're measuring a package's exact weight or a process cycle time. You're not just counting whole integers. You're dealing with precise, physical measurements on a continuous numerical scale. To monitor a process with continuous data, you absolutely have to look at your subgroup size. So, ask yourself, how many items are you measuring at one single time? If you're testing one single item sequentially, your subgroup size, which we represent mathematically as n, is exactly 1. And when n equals 1, the rule is absolute. You deploy an IMR chart, which stands for individuals and moving range. Since there's no subgroup of multiple items to average out, the IMR chart just plots the individual value and brilliantly calculates the variation by looking at the moving range between consecutive data points.
But hey, what happens if you take multiple measurements at once? If you're collecting data in small subgroups, typically between 2 and 8 items per sample, you immediately shift over to the Xbar-R chart. The X-bar tracks the mathematical average of your small subgroup over time, while the R, the range, tracks the spread between the highest and lowest values in that specific batch. Now, quick expert tip for you. If your subgroup size grows large, let's say greater than 8, you'd actually graduate to the Xbar-S chart, where standard deviation replaces the simple range. But for our core matrix today, Xbar-R is your primary engine for small continuous subgroups.
Moving right along. Section 2, the Discrete Data Pillar.
Welcome to the realm of attributive counting. We're no longer measuring physical parameters on some infinite scale. We're counting. We're looking at categories, attributes. Did it pass or did it fail? How many scratches are on this thing? This requires a totally different mathematical approach because the data is attributive. Entering this discrete world, the first tool we hit is the P-chart. The P stands for proportion. We use this when we're tracking the proportion of defective units with varying subgroup sizes. Think of a strictly binary go or no-go status. The P-chart answers exactly what percentage of our total items were completely rejected. The item is either entirely good or entirely bad. Zero middle ground.
Now, we've got to contrast this directly with the U-chart, which stands for defects per unit. While the P-chart tells you if the whole unit was ruined, the U-chart counts the total number of specific flaws per single unit, especially when your inspection area varies. For example, a single unit might have 3 scratches, 2 dents, and a tear, but hey, it might still be functional. When you're counting multiple individual flaws on one single item, the U-chart is absolutely the tool you need.
And this right here brilliantly illustrates the complete architectural lap. It's an elegant, foolproof binary decision matrix. Down the left-hand side, you determine your data DNA, continuous or discrete. Across the top, you determine your subgroup property. Does n equal 1? Is it small batches, binary proportions, or total counts? You just find the intersection, and boom, you instantly know whether to use the IMR, the Xbar-R, the P-chart, or the U-chart. There's literally no guessing involved, just pure statistical logic.
Section 3. BlueprintRM&Co. Case Studies. Theory into operational reality.
Because honestly, theory is totally useless without execution. We need to ground this framework in visceral reality by stepping into our premium e-commerce logistics environment at BlueprintRM&Co. Let's look at Case 1. We're monitoring the cycle time of our ultra-exclusive custom engraving line. Because these are highly bespoke, low-volume items, the orders arrive and are processed one by one. We want to measure the exact processing time. So which chart do we use?
A solid black belt instantly recognizes the DNA here. We're measuring time, right?
So that's continuous data. The orders arrive individually, meaning our subgroup size n is exactly 1. The decision is irrevocable. We deploy the IMR chart. We watch the individual values and track that moving range to keep our exclusive line in perfect statistical control.
Okay, case 2. Let's move over to the high-speed fulfillment line. Out here, we're sampling a batch of 5 random packages every single hour to check the total weight consistency. What's the correct statistical weapon for this exact scenario?
Once again, we rely on the matrix. We are measuring weight, so we're still firmly planted in the continuous data pillar. But now, we're pulling a fixed small subgroup of exactly 5 packages at a time. That subgroup size strictly dictates our selection. Because n equals 5, we deploy the Xbar-R chart. It seamlessly tracks both the average weight and the range of those 5 packages every hour.
Let's look at case 3. We are now standing at the final quality gate. This gate tracks packages that have failed final inspection and are classified as entirely defective, meaning they absolutely cannot ship. Crucially, the total volume of packages we inspect here varies from day to day based on customer demand. Which chart applies? Notice how the data DNA has fundamentally changed here. We aren't measuring physical parameters anymore. We're judging pass or fail. A package is either completely good or completely bad. This is discrete data. And because the status is binary over a varying daily volume, it perfectly matches the P-chart. We want to monitor the exact proportion of failed packages.
All right, case 4. Finally, we're auditing the visual quality of our premium wooden gift boxes. A single box might have 0 scratches, 1 scratch, or even 3 scratches, but it can still be salvaged and sent to the customer. The batches we audit vary in size every single day. We are counting the flaws. So, which chart? We are in the discrete data pillar, but we aren't throwing the whole box away. We're counting specific individual flaws per unit across varying batch sizes. This absolutely demands the U-chart. It is the perfect mathematical weapon for tracking the total number of defects per unit when your inspection area fluctuates.
Final section, the power of the right choice. Let's see how this all builds up.
Let's zoom out from the factory floor and take a boardroom-level perspective. Why does this rigid, unapologetic selection process matter so deeply to operational excellence? Well, it matters because of the math. When you use the right chart, your statistical software calculates control limits, your upper and lower control limits, at exactly plus or minus 3 sigma from the process average. Letting the DNA of the data totally dictate the tool ensures that these plus or minus 3 sigma limits perfectly reflect the true mathematical capability of your process. If you use the wrong chart, your limits are artificially wide or disastrously narrow, rendering your data completely useless. A Lean Six Sigma black belt never guesses which chart to use. By adhering to this strict decision matrix, you guarantee that your process stability is fact, not fiction. You eliminate false alarms, you identify true special cause variation, and you deliver bulletproof data integrity to the boardroom. So ask yourself, is your current operational data telling you the truth, or are you just using the wrong chart? For education and entertainment,